When we have a balanced chemical equation, the coefficients that balance the atoms on both sides of that equation give us the relationships between the reactants and the products. That is, they tell us the relative number of moles of the reactants that are required to carry out the reaction, as well as the number of moles of products that are produced in the reaction. Now we know that there is a relationship between the moles of a given compound and the mass, and this relationship is of course given by the molar mass. So because we know a molar relationship in our balanced chemical equation, we can also determine a mass relationship or a mass ratio of the products and reactants. And so let's do a couple of simple examples here. So in the case of the reaction of carbon monoxide with oxygen to produce carbon dioxide, our balanced equation says that we have two molecules of CO reacting for one molecule of oxygen to produce two molecules of CO2. A more useful way to think about this equation is that we have 2 moles of carbon monoxide reacts with 1 mole of oxygen to produce 2 moles of carbon dioxide. So it's most useful for us to think of these coefficients to represent the molar ratios. We know from the molar masses that can be calculated that carbon monoxide, 1 mole weighs 28.01 grams, 1 mole of oxygen weighs 32 grams, and 1 mole of carbon dioxide weighs 44.01 grams, right? These values are determined simply by adding up the atomic masses for each compound. So another way to think of the relationship within this balanced equation is to say that 2 moles of carbon monoxide weighs 2 times 28, or about 56 grams. 1 mole of oxygen weighs 32 grams, and 2 moles of carbon dioxide weigh about 88 grams, right? So it gives us this molar ratio. So we can solve some simple, what we call stoichiometry problems using this information, that is determining how much of the reactants we need to mix together and how much products we expect to obtain. So let's start with a very simple example. So if we wanted to know how many moles of oxygen are needed to completely react with 7.4 moles of carbon monoxide, we can calculate this by using these molar and mass ratios. We then want to calculate how many moles of carbon dioxide we would expect to get. So in these types of problems, we always need to begin with a balanced chemical equation. So again, 2CO plus O2 goes to 2CO2, and we have this molar relationship. And again, we are going to use these mole-mole ratios, these equivalent statements, as conversion factors to go from moles of one thing to moles of another. And so let's start with calculating how much oxygen we need. Okay, so we're given in the problem that we need to have that we start with 7.4 moles of carbon monoxide. So we have 7.4 moles of CO. Now we are going to multiply this by a conversion factor that converts between moles of CO and moles of oxygen, which is given again by this relationship. So we're going to say we want to determine the moles of oxygen. So we're going to put 1 mole of O2 on the top, and then we're going to divide that by 2 moles of carbon monoxide. I want to get a toolbar here. Okay, and when we do this, we see that our moles of CO cancel, and we're left with what we want, moles of oxygen. So we're going to take 7.4 and we're going to divide it by 2. So it tells us we need to react 3.7 moles of oxygen to completely combust this 2 moles of carbon monoxide. Now, once we've calculated the moles of oxygen that we will be required, we can calculate the moles of CO2 that we will expect to get. So we can do this either beginning with our moles of carbon monoxide. We could just as easily get it with our moles of oxygen. And I think we're going to do it both ways to assure ourselves of this. Okay, so to calculate, again, the moles of carbon dioxide that we expect to get from 7.4 moles of carbon monoxide, we are going to take this relationship, again, starting with 7 moles of CO, 7.4. Now we're going to see from our relationship that we get 2 moles of CO for every 2 moles of carbon monoxide that reacts. So it's a 1-to-1 ratio, but we can write a 2-to-2 ratio also. It's all the same. Okay. So 2 moles of carbon dioxide is produced from every 2 moles of carbon monoxide that reacts. So that is simple math. Tells us we're going to get 7.4 moles of carbon dioxide. Now we will get exactly the same answer if we begin with our moles of oxygen. Okay, so let's do it that way. We have 3.7 moles of oxygen, and we produce 2 moles of carbon dioxide for every 1 mole of oxygen that we react, right? Again, these are our mole-mole ratios given up here in our balanced chemical equation. So now we're going to take 3.7 times 2, and this will, of course, give us the same answer, 7.4 moles of carbon dioxide. Now this was a very simple example, and in the next video we're going to go and convert grams of our product to grams of our grams of our reactant to grams of our product. One important thing that we want to remember while we're doing these problems is it's very helpful for us to be very explicit about the units as we're writing them, and that will prevent us from getting confused. So making sure that when we convert moles of oxygen to moles of carbon dioxide, that we're clear that we're converting 2 moles of CO2 and not making some sort of simple mistake.